All right, so let us just start here at our separatory techniques. All right, should be really fun. It should be really fun actually. All right, so our techniques for solvent extractions should be fine. So let's have a look here. Now, the separatory techniques that we normally look at, we know simple distillation, fractional distillation. We should know like a separatory and funnel, etc. Right? So key information, right? We must know the fact that distillation under reduced pressure is used to distill compounds, which may decompose if it's distilled at high atmospheric pressure. Steam distillation is used to separate mixtures of immiscible liquids or to extract oils from plants. Steam distillation is also used to purify high boiling point liquids such as phenylamine and nitrobenzene, right? So those are some things that we looked at as well before Module 1. Solvent extraction is based on the relative solubility of a substance in two miscible liquids, right? The distribution coefficient is the constant at a particular temperature which relates to the concentration of a solute partitioned between two immiscible solvents, right? So we're just looking at this is all the key information that continues to re-show itself throughout the entirety of the PowerPoint. The amount of solute extracted from a particular solution by another solvent can be calculated if the distribution coefficient is known. 7. Several extractions using small portions of solvent are more efficient than using one very large volume, right, of solvent. And finally, distillation is applicable, right, to distillation in the petroleum industry, which is fractional distillation, the rum industry, which is column distillation, the fragrance industry, which is solvent extraction, steam distillation, vacuum distillation, and fractional distillation, right? So let's have a look at this. Vacuum distillation, which is a simple distillation under reduced pressure. That is what vacuum distillation is. So the advantages of carrying out this type of distillation, right, speaks to the fact that it reduces pressures below 1 atmosphere, right? So the reduced pressures result in lower boiling points as many components cannot be distilled at atmospheric pressure because their boiling points are too high and they will decompose. So if we decrease the pressure, it will also decrease the boiling point, right? And stop it from decomposing, stop it from reaching that decomposition point, right? We can purify phenylamine, right, by distilling impure phenylamine under reduced pressure. The boiling point of phenylamine is reduced to 77 degrees Celsius after its original 184 if distillation is carried out at about 0.02 atmospheres. Right? The syllabus specifically asks us to look at phenylamine and nitrobenzene, so please know it. Right? Also, the reduced pressure decreases the energy requirement for both the heating and cooling processes, right? So the solvent dimethyl sulfoxide, right, is commonly purified by vacuum distillation because it is more stable when distilled under reduced pressure. So this is all about stability. The reason why we use this is because at atmospheric temperature, that would actually lead to decomposition if we try to distill it under those high pressures, under those high temperatures, right? So we reduce the pressure, and that will in turn reduce the boiling point of the substance. All right? Does that make sense? Make sense so far? All right. Steam distillation now. In a mixture of two immiscible liquids, they will exert vapor pressure independent of each other. Right? We must know that. Right? For example, plant oils and water are two immiscible liquids. They do not mix at all. So recall boiling point is the temperature at which the vapor pressure is equal to the atmospheric pressure. Please note that. That is what boiling point is. So instead of doing the simple definition of boiling point is the temperature at which a liquid boils. What is boiling? It happens when the vapor pressure of the liquid surpasses that of atmospheric pressure. That is what a boiling point is. We are at Cape, therefore we must have a more intricate understanding of these terms. An immiscible mixture will boil at a temperature below that of either pure liquid, right? Of their pure liquid rather, right? For two immiscible liquids, the total vapor pressure is equal to the sum of the vapor pressures of the pure components, Dalton's law. So we saw that already, that is Dalton's law. Okay. So for steam distillation now, right, we'll have phenylamine that boils at lower than 90 degrees Celsius there, and boiling point of water is 100 degrees Celsius, right? So we can look at this now. So we have the mixture of water and phenylamine boils at under 98, but pure water is 100 and pure phenylamine is 184. So notice when you mix them, the boiling point decreases, right? And we tend to use steam distillation for this, right? So that's how you set up a steam distillation apparatus here. Alright. So what we do, we heat the solution. The solution pumps the steam through the compound being distilled, and then we're gonna have the collection of the more volatile compound. Alright. Uses of steam distillation now. Extraction of essential oils from plant material, that is important. For example, eucalyptus oil, citrus oils from peels, pimento oils, etc. are some of these substances decomposes, right? Some of these substances decompose at high temperatures, right? So, well, at temperatures below the boiling point of, at atmospheric pressure, right? So this would be temperatures that will actually they decompose at low temperatures rather, right? That's what I'm trying to say, right? So if you try to really increase it to a certain temperature to actually reach a boiling point, all of these essential oils would actually start to break down. So use steam distillation rather, right, in order to get it distilled without reaching such a high temperature to destroy the substances, right? So usually it's used in the purification of some organic products from aqueous media, right? And that's where we get our eucalyptus oils and stuff like that, our general essential and plant oils. All right. So because they're easily decomposed at temperatures below boiling point, we use steam distillation in order to distill it rather than heating up the entire solution to boiling point. We'll also have the separatory funnel, right? So something that you guys should have done experimentally in your labs before, right? That's quick separatory funnel, right? So we would have a stopper, we would have the funnel would have a stopper, and the low density liquid will sit on top of the high density liquid, and then you have the stopcock, right? So you guys know how to use this, right? It should be fine. So the separatory funnel now. A separating funnel is used to separate two immiscible liquids, as we know already. If left to stand, the denser liquid will form the lower layer and the less dense liquid will form the upper layer. They can be collected separately. So that makes sense. So if they collect in two different layers, all you do is let out the bottom layer, right? And then close the stopcock. So it should be fine. This one should make a lot of sense. It should be okay. Alright? Solvent extraction now. If a substance is dissolved in a solvent in which it is not very soluble, it can be extracted from this mixture using a solvent that is immiscible with the initial solvent but is able to dissolve the desired product. What does this mean? This means that if we have a solution up here with a solute in here, right? It's not really soluble, right? But let's call that solution A. But we add solution B here, right? This substance is actually way more soluble in solution B. What we can do is drag out the solute, right, into solution B and then separate it. So this is how we are able to extract things from different solvents, right, using a more suitable solvent, right? So here is where the entire partition coefficient comes in. If a substance that is soluble in two immiscible liquids is added to a mixture of the two, there will be a partition, right? So they will partition themselves, or it will partition itself between the two liquids based on the relative solubility of the two liquids. For example, if we shake aqueous ammonia with equal volumes of trichloromethane in a separatory funnel, ammonia molecules will move between both layers, right? Until an equilibrium is established. Alright? The concentration of ammonia in each layer will be determined by titration. Right? The equilibrium constant for this process is called the distribution coefficient, or what we call the partition coefficient, Kd. The value of Kd may vary with temperature. Okay? So notice that all the information as it relates to the coefficient is here. You can't say you did not get the information. You have to have the information, right? So we're gonna have an equilibrium being set up between two liquids, right? Between two of the solvents, right? And looking at that equilibrium constant for this equilibrium, it will be Kd, which will be the aqueous phase divided by the organic phase, right? So an example here, a solution of butadioic acid BDA in ether contains 4 grams of BDA and 20 centimeter cubes of ether. This solution is shaken with 50 centimeter cubes of water. Calculate the mass of BDA extracted into the water layer, the aqueous layer. Right? So Kd for BDA in ether, right? Um, in relation to BDA in water is 6.7, so that is given. So to calculate the concentration of each component now, this is what we shall do. We shall use the mass in dm³. We shall use our mass concentrations, right? Generally, right? Well, it's actually our mole concentration. Rather, we're gonna get the mass and then we're gonna convert that to moles, so we can get our molar concentration. And once we get our concentration of BDA in the aqueous phase and our concentration of BDA in the organic phase, we put aqueous over organic, and that is how we get the Kd. When we evaluate now, right, that is when we're going to get the general mass, which is 3.8 grams, because we need to change moles back to masses in order to get our original mass there, right? So if M is the mass of water, this must have this must have come rather, right, from the ether layer. So M is subtracted from the mass of the ether layer, right? So we have that there. So if we have some amount of BDA in the water, right, that must have come from the organic layer. Because what we're saying is that we have substance of BDA in the organic layer, right? And then what we do, we mix it with water. So it's gonna form this partition, right? That means that any BDA we find in water, this is H2O, and this is going to be our BDA, right? That means that any solution, anything that you find in the water has come from the organic solution of the ether here. That makes sense, right? Does that make sense? If you have BDA in ether, right? If you have the butadioic acid in ether, right? And you mix it with pure water, that means that any butadioic acid that you find in water come from the ether layer, right? So the mass that we're finding in the aqueous layer is actually going to be subtracted from the mass, overall mass that was in the ether layer, because that mass would have gone, some of that mass of BDA in the ether layer will actually be moving into the water, right? That's what's happening there. So another example of the partition coefficient, here several extractions using small portions of solvent are more efficient than using a large volume of solvent. We can see this by comparing two solvents, A and B, where Kd of B over A, right, is 4. That is the theoretical value. 15 grams of the solute in 50 centimeter cubes of A is shaken with 50 centimeter cubes of B. Calculate the amount of solute transferred to B. Right, so it's gonna be generally the same thing. The mass in the aqueous will be divided by the mass, right, in organic minus the mass in the aqueous. We're gonna get that. All right. Now, if we extract the solute using 2 portions of 25 centimeter cube, we're gonna get a higher value, right? So we're gonna get 10 first, then we're gonna get that 3 first, and we're gonna actually get 13.3 grams extracted, right? So just let me know if I'm moving a bit too fast or you have any questions. The reason why this flows for me is because I've done these experiments time and time again, right? So I know exactly what this is, right? So if you're not getting it, please ask. All right. All right. So that is generally what's happening here for the partition coefficient here. All right. So before I move on, does the partition coefficient thing make sense? Well, I'll know if it makes sense because I'm gonna propose 2 past questions to you guys at the end, right? So the information is here. literally how stuff are done is here. I know that some people don't have issues with the content, but how you approach a question is a problem. Notice how I gave you two ways to approach a question. Don't tell me that you can't do the questions, all right? So let's have a go at this now. Methods of separation based on physical and chemical properties now. Selecting a suitable method of separation depends on the solubility, boiling points, right? Solubility and the boiling points, right? So the solubility and insoluble solid can be separated from a soluble solid by dissolving the latter, then filtering. Boiling points now, a mixture of liquids with different boiling points can be separated by fractional distillation. Solubility in different solvents now, we use solvent extraction. Notice how this information is listed neatly. So if I propose to you a scenario tomorrow or within the week, right, in the WhatsApp group, you must be able to tell me the suitable method, the most suitable method, right, of solvent extraction. Here are all the methods that we use, and they are here in front of you. Can't say enough to them. All right. I want you guys to have the information, use the information, go and get that exam over with. All right. So applications of distillation methods used in various industries, right? This is really a question to you, right? I want you guys to have this information. If you look for it, you're gonna internalize it a little bit better. So name and explain the application of distillation methods in the following industries: the petroleum industry, the rum industry, and the fragrance industry. These are actually listed at the beginning of the presentation, right? They were all listed actually. In your answer, cite examples of compounds or raw materials used to give equations where necessary. Used and give equations where necessary. All right. So in petroleum industry, what type of distillation do we tend to use?
Fractional distillation.
Lovely, fraction distillation. In the rum industry, what do we use?
Same fractional distillation.
All right. Fragrance industry.
So I think you said something about solvent extraction.
We can use solvent extraction, or we're looking at the type of distillation. So what type of distillation? Remember, in fragrance industry, we're extracting things from plants. So it is, and the plants will, the substances that we get from the plants, like the eucalyptus and the cinnamon, and the different types of fragrances in perfumes, right? These things break down quickly, right? They have low decomposition temperatures. So what type of distillation that we use? Vacuum. We use steam. Steam is most likely used, but we can also use vacuum distillation. All right. So if they come to you with any type of question, any 4 mark or like 8 mark question talking about distillation and stuff like that, you guys should be able to examine the question, note the properties of the substances, right, or note the distillation used in the industries, and be able to know, provide to me an experiment that we can use. So if Mr. Brown, right, wants to extract citronella oil from lemongrass or from fever grass, as we call it in the Caribbean, right? What type of distillation will he use? And give us an explanation, set up an experiment, right, that he would use in order to extract the oil from this plant. Then this is the time where you as a student must be able to provide us how, right, or the setup for a steam distillation, right? So you must be able to do that, especially if we speak about the fact that we're combining a solute, right, with two different solvents, right? How is it we separate them? How can we separate them, right? You need to define the type of separation that we use and set up an experiment to actually extract the solute. In this case, you need to have enough information and knowledge to know that we're going to be using solvent extraction, liquid extractions, and then we're going to use a separatory funnel. I know you described the experiment of how we use a separatory funnel and the knowledge of the partition coefficient to purify that solute that we will get, right? There is a method to the madness. You guys must be able to use these things properly to answer the questions. right? So the key points stand again, and here are now some more questions. If you can answer these questions, you are well on your way. Explain the chemical principles of following. You must explain the chemical principles behind steam distillation and vacuum distillation. State the advantages of carrying out the processes above. Define the term partition coefficient. And in number 4, benzene is immiscible with water. When 50 centimeter cubes of aqueous solution containing 0.5 grams of organic solute X is shaken with 5 centimeter cubes of benzene, 0.2 grams of the solute X is extracted in the benzene. Calculate the volume of the partition coefficient, the value rather of the partition coefficient of X between benzene and water, 4 marks. So if you can comfortably do these questions, you comfortably understand the topic, right? So have a go at those questions, right? We also have past paper question 2013. Simple thing, define partition coefficient. You cannot lose that mark. You cannot. Simply cannot. And B here, right, is similar to the question that I posed before. And how you do the questions are in the PowerPoint. Here are the two general methods that we use. We have general method 1 here and general method 2 here when you're provided with different types of information. So the information is there that you can use to help to get the answer, right? You also have past paper 2016 and aqueous layer right here. You have the partition coefficient of water there, right? Calculate the mass of the component extracted by shaking 100 grams of aqueous solution with 25 centimeter cube of solvent. These things should be fine. You guys should be able to do these things, right? So go through the information, have a look at the questions, and please do try. All right. So that is generally it. Are there any questions or concerns that you guys